right, I'm testing the audio. Let's just make sure. All right. It sounds like it's working. So we left off last time with this particular problem that we worked our way through. It was worked right here. And we went through the whole sequence, even to the point where we did something interesting. Let's go and look at the problems that are associated with this section. Now, the problem is, okay, things don't exactly line up. Oh, here, let's do the word of the day. Excuse me. Needle. Now, that's not a good word. Truck. There you go. That's the word. Oh no. What do I got to do? Chimney. Let's see if it verifies. It's going to tell me. Oh, okay. So let me try to find out which week these problems are in. I'm not guaranteeing that I'm lining up on the weeks. The lectures are lining up on those weeks. And here we see some of this. Let's look at homework 5. Homework 5 might be a little further along. So let's go back here. This is in dynamics. Let's go back to 4. Okay. I think there was a set that I used. I think this is the set. Yeah. Okay. See what I'll do. I'll drop these things out of here and we'll look at them individually. Okay, so what I'll do is I'll drop it. I'll just save it there. Show in the folder. Double click. Should launch it right there. All right. So here, let's start with this one. Okay, the magnitude and coordinate direction angles of F so that the resultant of the three forces is 0. Okay, so here we go. So all you do is first thing you're going to do, you obviously have an F1 and you obviously have an F2. So let's attack F1 first. It's just going to be, oh, that's the easiest thing. To me, it looks like F1 is going straight down that direction of a minus 180. Is that right? Yeah, 180 I. Now F2 is, and here's that double projection thing. So in this thing, you imagine the sunlight is coming from below and it projects this vector to this plane right here. So this is dropped below the plane. The plane I'm talking about is this plane. So there's the plane I'm talking about. So we want to know the length of that. So what is that? Okay, I say a 30-degree angle there. So I say cosine of 30 times the length of that 300 is the length of this one. So I'll just pull that out to the side, and I will do Alt-Tab until I can get to this, and then I'll do clear first and clear the screen, and then I'll do 300 times cosine in degrees of 30, 259.81. 259.81, and that's the length. The vector, it starts here, ends up out here. So if you want to put an arrowhead on it, it's like this. Now what I've got to do is I've got to come across and find the equivalent vector here and the equivalent vector here. But then I also have to, let's see if I can do this. I have trouble doing this in this application, so I'm just gonna do the best I can about mimicking it. So what I'm trying to do is make a plane, and that's my plane there. So if that's 259 and this appears to be 40 degrees, then this appears to be 259.81 cosine of 40, and I wrote 30 for some reason. And that means this one is sine of 40, and that's the angle in that plane. The 30 brought us up to that plane. So if you look at this thing at this point, what you're seeing is all three components in there a little bit at this point, not completely, but almost completely. Here's what I mean. I got a Z component that's going down. I haven't dealt with that yet, but I'm going to go ahead and deal with that. Now, what this is imagine looking at this. Sorry, my hand went awry there. And gosh, this looks so funny looking. And this is the 30 degrees right here. So at that point, this has got to be, what is it, 300 pounds sine of 30. And now let me see if I can lay that out a little bit better. Unfortunately, you know what? I could probably go back to the book and write in the book, because the picture is probably better in the book. I wasn't at that one, but I saw it. Oh man, I think maybe I thought I saw it, but I really didn't see it. Maybe I didn't see it. Okay, so I take that back. Let me go back to the thing. I thought I saw it, but I guess I didn't. I don't know. So I'm sitting here looking at this, and now I realize, gosh, that's messy. So this is F2, and I've obviously got an I component, and a J, and a K. Now, I'm putting a plus, but I can tell you already, this component of this force goes down in the Z direction. So, did I find the actual value here? No, but I think I'll do that real quick. Now that I got that 259, I'll just call it A. Sorry. Excuse me. So let's see. A, which is, let's see if I can roll this. Yeah. Times sine. And I did not put the multiplication symbol. I missed the shift key. Sine in degrees of 40, 167. So let me just write that, 167. That seems pretty interesting. I don't think that's going to be that interesting for the next one. Well, okay. I take that back. I guess it is interesting a little bit. 199. And I could throw away the digits. So I think I'll do that. And I don't think I figured out this one yet. That one should be 150. Oops. So this one's 150. So shoot, I wish I was in the other thing. I could change this around. So 167. Okay, so it's going down 150. It's going over to the right 199. Now, I threw away some digits, so I don't know how accurate I'll be compared to what he would ever come up with, but I'm just going to go with it. And I've got so much crap on the screen there. Now he's saying this F3 has to be pulling or moving in such a direction that the resultant of the 3/4 is 0. So F3, and then what you do is you say F1 plus F2 plus F3 equal to 0i plus 0j plus 0k. Well, I'll start with this one. That's got to be that. And it's got to be, 150. Now this one I need to figure out. So here I'll take the 180, or how about the 167? Well, if you go 170, that's a 13 difference. So if I added 13 to it, and again, I'm not doing very good as far as carrying the decimal points, but let's just check. Does 180 plus 167, whoops, minus 180 plus 167 plus 13, what's that equal to? And yep, it equals 0. So now, did I even include the answer here? Yeah, it says 250, and I'll address several of those in a second. You know what? I think what I'm going to do is make use of Octave's ability, or MATLAB, or whatever, his ability to figure out things for me. So what I'm going to do now, there's a good chance I made a mistake. I'm not really with it too much today. Okay. We'll find out if I made a mistake. Well, 249.54 is pretty close to 250. Now, how do you find the angles? Well, that's actually pretty simple. If you have any vector, which the vector he's interested, I guess, so that determine the magnitude of F3 so that the resulting force is 0. So he wants to know the magnitude, which is about the 250, and the coordinate angle directions. So again, what that is, and I'm going to make a half-hearted attempt at doing this. I'm going to try to draw this one. Okay, so he had X going this way. He had Y kind of going this way. He had Z going this way. Now, boy, 13 is a very short So I'll tag it. So I'll tag this one at about 13. I'll tag that one at, wait, I'm tagging this one at like 199. And I'm tagging the Z at 150. So I don't know that this is to scale, but these are my 3 points. So again, in the other application, which I guess I should have moved this one over to it, I could make these lines and copy them here. And obviously I don't have very good ability to okay, so there's my box, and the box is 150, which is that one, 199, she goes into the back, goes backwards, and then 13. Okay, now I had the other app up and doing it in there. I could use the ruler, but I don't. And this vector needs to start here, oh gosh, and end up there. So that's okay. I did a fair job. So there it is. Now, first thing I can tell you by looking at this is the angle from the first one. Alpha is going to be slightly less than 90 degrees, because if this vector head, instead of landing here, let me try to make this a little bit better. Okay, I know I have a ruler in here somewhere. If I can lay the ruler or just a piece of paper, I got an idea. I've got a card right here. Shrink the screen down to the point where the card will fit on there. There we go. So there is the vector. If the vector pointed to this point, then it would be 90 degrees. In other words, if you took off the 13 and you had a vector that went to right here, in fact, alpha would be 90, but it's moved away from that plane a little bit. So it's going to be slightly less than 90. Now, of course, beta, the angle, and what these are, here, let me kind of say. This one's alpha. Let's see if I can get a decent job here. This one, these are 3-dimensionals, beta. And this one is gamma. Well, beta, you're going to be much larger than 90, because if it landed in that plane, if it landed in, the vector landed in this plane right here, then in fact it would be 90. Well, it's way behind that plane. And so gamma, what would be gamma, you think? Well, it's definitely going to be less than 90, but I don't know exactly. So I'm kind of getting a feel for it. Now I'm going to go find it. So how do you find it? Basically what you do is you look for the normal in the direction of it. How do you find the normal? And I guess I'll just call it normal. Okay, let me rephrase what I just said. Not the normal, the unit vector in the direction of this. So if I want to know the unit normal, the unit vector that points in the direction of that, golly, you get this vector over the length of it. So that's actually not that hard to come up with if you have something like this sitting in front of you. First of all, I need to be able to, I already have F3. I've written F3 in there. So if I want to know the unit normal, not the unit normal, but just the unit vector, gosh, it's not normal to anything. F3 divided by the norm of F3, I get those numbers. Now they look kind of funny, and they'll always kind of look that way a little bit. So I'm going to bounce back and forth. 0.052 okay, minus 0.797. You know what? Okay, 469 plus 0.6. Oops, there's supposed to be a J right there. 0.601107K. Okay, so if you want to know what these vectors are, you look back in the book and what you'll find out. This angle can come from this component. This one can come from here, and this one can come from here. So in fact, I've got a unit vector. So in other words, okay, depends on how you, some people list this in books as 2096. Okay, if you look at it, some people list it like this, other people will list it like that. Octave can't do that, so it's got another way of doing things. So let's take a look at it. If you go in a cosine, and I want the answers in degrees for all of these, I just take the unit vector. These are your numbers. Now, did it end up what we thought it would? And there's two things. Let's look at whether it fit our pattern. Did it fit our pattern here? Is beta greater than 0? I mean 90, greater than 90. And yes, the second term is greater than 90. The first two terms are less than. This one is pretty close to 0. I mean pretty close to 90. And the reason being is because if this were 0, then this would end up at 90 degrees. And I can show you an example of that, but I'm tripping over my own words here. So what I will come back and do here is you can do this. Cosine inverse of U3, which is what I just did, and you can get your three angles out of there. Now, instead of writing them down, you know what I'm going to do? I'm going to go right here, and I'm going to compare the 87 here to the 87 he has over on the right here. 142, he said 143, 53. So you kind of get the idea. Okay, that one's okay. Express each force. Is there another problem related to that? No, there is not. Okay, so this is a fairly simple one. You're just wanting to express everything as Cartesian. F1 is equal to something I plus something J plus something K. And F2 would equal to something I and F3 would equal to something I plus something J plus some sort of coefficient of the K. Really the easiest one, I got this one just be pulled straight up at 200, and so we'll check that one. Yeah, he didn't list any of the other two. And so the other, this one, I'll do this one, then leave you to do this one. The procedure is the same on this one, and I'll just say, imagine there's a sunlight above it, it hits this thing and casts a shadow on the ground. This is the shadow arrow. How do you get it? You take the original arrow, which is 150, times cosine of the angle that you have here. It's 60, sorry. And then what you want to do is project that over here, so you'll have this component, this component. Now that'll give you the X, this, like, what is this called? F2. The F2 in the X direction. This will be the F2 in the Y direction. How do you get the Z? Well, what you do is you imagine you're looking at this plane. Okay. So in other words, I'm looking at this plane. And as I look at that plane, so I'm using this shading the same way he's using it. So that's all green. So that's your plane right there. And in your plane, you got 60 degrees. You already used, and this is a length 150. Whoops. There's a length of 150. So you already used the cosine. So obviously this length from here to here is the same as the length from here to here. Depends on the way you want to do it. Most people put it here, and then they'll just tell you that's 150 sine of, what was that, 60. And that gives you 3 components. This one's even easier. This one right here. In other words, that's 90, right? So let me get rid of this. And we'll get rid of this. And we're focusing on now finding the components here on this F1. So what you've got is you got a component here and one going here, but you have nothing heading to the right. There is no component that way. It's in this plane. And he's indicated that by putting this box around it. He didn't color it, but he should have, and the color should sit right here. This is your plane. So I lost something there. Anyway, I had a vector here. So in that, there's 4 fifths. Okay, this is 90. So 4/5 of 90 goes right here. And 3, which is going vertical, so it's this. 3/5 of 90 goes there. So you're all good there. So I'll let you hammer the rest of that out. Here is some sort of bracket. Okay, so find the magnitude and the coordinate direction angles of the resulting force. Okay, so he has 2 of them. Let me just see what else is down here, see if I do a repeat. Okay, there's no repeat. In other words, the same picture is used twice. So in here, you've got to do F1 listed out, and then F2. Well, for me, I know F2 comes after F1 because 1 comes after, or 1 comes before 2, but I'm going to do F2 first, simply because he just laid out the angles for me. So that's like a no-brainer there. So what F2 is 400, because that's his size. And cosine, and I don't want to write 400 over and over, so I'm going to put a bracket around this thing. Cosine of what? Cosine of the angle between the vector and the x-axis, and that's 120. 120i plus the cosine between the angle between the vector and the y-axis, and that's the 45. And then the cosine of what's left, but it's between the z-axis in the vector, which happens to be 60. That's it. So all you do is take the cosine of that, put it there, cosine of that, multiply it times that, and go on and go through that. So in fact, this is the unit vector in, I'm writing it down because I've verbally said it in a weird way. Unit vector in the direction of F2. Now let's just take a minute and prove that it's a unit vector. So here's what I'm going to do. Clear. And I'm going to say, I got three angles, alpha, beta, and gamma. I'll call these things A for angles. I have 120, then I had 45, and then I had 60. Oh, and I was going to put a bracket around it. Now, I want my unit vector equal to the cosine, and I have to put degrees because I'm putting this in it, of the angles. And there's my unit vector. Now, before I say anything, let's make sure it is a unit vector. Yes, it's of length 1. And so, if you think about it, this is exactly what's happening in reverse. This defines the unit vector. You've got two ways to define it. And here, let's do it this way. It is, and I guess I'm going to specifically talk about it in the context of F2. Well, in this F2, that's 400. And now let's list this. This is 400 times all of this stuff. And here, I'll just do it like this. I don't know this is going to work. I really don't know. Okay, it did kind of work. So, okay, now I have to hit the escape button. Yeah, it goes away. So essentially that's the case. Well, it cancels the 400. And hey, wait a minute. Now, so you're saying the unit vector is in fact cosine of alpha I plus cosine, which alpha was the 120. I'm going back to kind of a symbolic beta j plus cosine gamma k. And beta was 45 and gamma was 60. So in fact, these are intimately related. Having all three of these angles tells you you can find that unit vector like almost instantly. Let's see. I don't know if this is making noises when I'm trying to erase. This one doesn't erase as nicely. You know, let's try this. I'm going to try, if I push this down, oh, it doesn't. Then I can do a delete maybe. All right. Okay, in F1, kind of interesting. Of course, I don't need any of these upper angles because what it's doing is you got a plane here. Although he's done this in a weird way. Technically, it should be like this. But what I'm going to do instead is say I'm going to ignore this part of his vector and say the vector ended right there. So if you project this vector up to here, then you can break it into the component here and the component here. So this vector, being the projection vector, would be 250 because that's the magnitude here. And it looks like, to me, it's projected up through an angle of 35 degrees. Which is a very strange angle, but that's okay. Now, you've got the situation where let's just project it over here onto a vector right here. Now, this one's 25 degrees, and so you can take this a couple of different ways. One, you could work off the triangle here, where that's 25, and actually, if you're looking straight down, you would kind of notice this line goes across here. Actually, if you look straight down, you'd find that. So what you would find is a triangle, which that is the hypotenuse, and it's 25 degrees, and you want to get this. So this, in fact, would be 250 times cosine 35, because that's what this one is, times another cosine of the 25. Now, I hadn't calculated any of that out, but then somewhere along the way, you're going to want to know this one. So that's still the 250 cosine of 35. And I'll tell you what, I'll highlight this. This is the projection vector. But it's also got to be taken through that 25 degrees here. And so it's actually sine of 25. Now, with those, this becomes F1, the x component. This becomes F1, the y component. Now, what do you do about the z? And as it turns out, I wish I'd, in the future, I think I'm going to pop these over onto OneNote and use them only on there. But I haven't done a good job of lining up the axes here, but let's take this vector and try to parallel it like so. I'll get this one out of the way and that out of the way. So at this point, I'm looking at a plane here, and that plane happens to be this plane. Now, technically, yeah, I should have it lined straight up under there, and in fact, let me see if I could fix that a little bit. It should have lined straight up there. And that these should have come together back here. Okay, so now I'm looking at this plane. And we already used the 35 degree here to work our way. Oh, that's interesting. We've already used our 35 degree to work our way to the point that, I guess if you want to get rid of that. Oh, there, it all goes away at once. Wonder what that is. Oh, okay. I had an extra color there. And I guess I can add extra colors and other things. Okay, I'll worry about that later. So, I want to know the component this direction, because this is the z direction. Well, it's the 250, and it's going through 35, but it's the same distance as this. Again, that's the hypotenuse. And it depends on the way you want to do it, but it ends up being, this 35 will take you up to here. This is actually 250 times the sine of 35. Is that right? 35, yep. That's your z component. F1 in the z component. So once you figure out those three numbers, this one, and this one, you can write them in the equation. You can add them together and determine the magnitude and the coordinate direction angles. Again, the coordinate direction angles come back to if you have any vector, say, any vector B, for example, and you want the unit normal, not the unit normal, the unit vector in the direction of B is just B over the magnitude of B, which is in fact the same thing as cosine alpha I plus cosine beta j plus cosine gamma k. Some books, not ours listed as alpha, beta, and gamma. You'll find some books list it like this: theta, x, and b, the angle between x and the b vector. And this one will be cosine of the angle between the y and the b, and the cosine of the angle between the z and the b vector. But our book, and it's probably just fine the way our book is, but other books will designate, and math books do this too. They designate the two angles your angles are between two different vectors. So once you find the magnitude, or once you find the resultant force, which is nothing more than F resultant is equal to F1 plus F2, once you take all these F's over here and you make your F1 out of it, you add them together and you'll get the resultant. Well, at that point, if you, I'll leave that for a minute. You want to know your unit vector in the direction of the resultant. It would be this, which is nothing more than the cosine alpha I plus cosine beta j plus cosine gamma k. Now I think what I'll do, I'll just delete that out and I'll move that up. And so that's pretty much it. Okay, escape key, that's right. So you find the vector, you find its magnitude, you take the vector and you divide each of the components by the magnitude, and you got each of these terms, and then you take the cosine inverse. And I'm speaking through a MATLAB sense now. Oh, I thought that was a disc on the screen. That's actually a mark. That will give you, in our case, alpha, beta, and gamma. And so here's your, okay, so he lists each one of these. You can check yourself. He lists the resultant, then the magnitude of the resultant, and then the angles there. So if you take 113 divided by 485, take the arc cosine, you should, or inverse cosine, you should get 104. You take 468 divided by 485, pretty close to 1. If you got 1, you get a 0, but you don't, but you got closer. So this is definitely closer than that. So you get 15. He's saying 56 over 485. Take the arc cosine and get 83. Okay, nope, 2 more. I don't think I'm going to be able to finish all of them here. So here you have F, B, and C. got 560. You got 700. This is, hey, wait a minute. I think I did this one already in one of the lectures. Yeah, I sure did. So this one was already done in a lecture a couple days ago. So look back at that. So I'll do this one instead. Determine the magnitude and direction angles of the resultant force acting point A on the post. Oh, okay. He's listed this one really, really strangely. So what I'm going to do is this is just me, this is my approach. I'll draw a vector to the top of the post. That's pretty easy. I think I see a 3 meter, and it's K. Then I would draw a vector to C and then to B. I'll just do B first because it's listed kind of straightforward. So B, vector 2B, is if I want to go from this point to B, I'll go out here 2, and I'll go across here 4, and then I don't have to go up or I don't have to go down. So that's it. Now what I've got here, if I am drawing a vector to C, he's got an interesting thing here. You got to stare at this really hard. Okay, so let's look at this. I know when I get in close, it kind of becomes pixelated. So to me, he's telling me it's 3 meters from here to here. So if he compares it to that, so that means if it's 3 meters there, it's 3 meters here. So if that's 3 meters, that's got to be 4. And then that's got to be 5. So what I'm going to do is, now that I see that, I'm going to transverse down that thing. Now I'm going to first go down the X. I'm going minus 3I. Then I have to go this way, which is a minus 4J. Now I don't have to go up or down because it's in, yeah, had to think about that for a minute. There's my 3 vectors. The next, that I've got. The next thing I want to do is I want to draw a vector from A to say B first. Okay, so let's do this. Again, I'm not drawing straight lines, so here's one vector. Here's the other, and now let me get all the extra stuff off there. As a matter of fact, here, let me just. Okay, here we go. Got this vector. That vector. The way I've written it, I've got this one is R A to B. This one is R B. This is R A. So this equation should read, if I go out here first and then down here, I get the same direction as if I go here. So that means RA plus RAB equals to RB. So now I want to know that. So what I do is take RB minus RA. So what I can do is just sort of glance back at these and say, take RB minus RA. So I take, here's A, RB, this one, minus that one. So I get 2I plus 4J minus 3K. Now if I want to find the RAC, I do a similar thing, and what I'm doing there is I go minus 3I minus 4J minus 3K. Okay. So now what I want to do is find a normal unit vector in the direction of, let's see, AB. And it's going to be RAB over that. And then I can find the unit vector AC. Is that right? Yes. RAC. Oh, we ran out of time. Let's go ahead and close it out. I just got to notice. We'll pick this up exactly where we left off. Because when I bring this up, it'll be right there. All right. Wait, did I do the word of the day? Here, hang on, shoot. Let me look. I'm really messing this one up here. Here, I'll look on the other computer real quick. Oh, I did. I did the word of the day. That's correct. Okay,